the incredible, almost invisible engine that powers our entire digital world, the computer chip.
Right.
For decades, these tiny marvels, they've just grown exponentially in power following this roadmap that, well, it's felt almost like a law of nature.
You're thinking, of course, about Moore's Law. Gordon Moore, co-founder of Intel back in '65, made this really remarkable prediction that the number of transistors on a chip would roughly double every 2 years. And you're absolutely right. It wasn't like a law of physics.
Yeah.
It became more of an economic thing, an industrial roadmap, kind of a self-fulfilling prophecy, really,
Right.
that has underpinned the whole information age. It drove relentless innovation for, what, over half a century now?
It's just astonishing when you stop and think about it. I mean, the phones in our pockets, the supercomputers, all the smart devices, they exist because of this exponential growth. It just consistently delivered. But here's the thing. The critical point we've reached now, this golden era of scaling, it's hitting some really fundamental barriers. Physical ones, economic ones.
Yeah.
Silicon, the bedrock material for chips, it's pushing right up against its absolute limits.
And this isn't just like a slight slowdown. People need to understand that. It's a really significant inflection point for the whole semiconductor industry, that historic doubling time.
Which used to be, 18 months?
Yeah, 18 months, then stretched to 2 years, maybe. Now it's pushing 3, even more in some cases. The classical physics that worked fine for larger devices, well, it's giving way to quantum effects, thermal problems.
Things silicon just can't handle.
Things silicon just cannot overcome at the nanometer scale we're talking about now. Yeah.
So are we really just stuck? Is this the end of the road for smaller, faster chips? Or is there something new, a radical new direction?
Oh, not a chance. Not stuck. A truly radical new direction is definitely emerging. Two-dimensional materials, 2D materials.
Yeah.
These are substances stable as just a single atomic layer, incredibly thin. And they're stepping up as, well, the most promising candidates to carry that spirit of Moore's Law forward.
Single atomic layer.
Yeah. We're talking specifically about a class called transition metal dichalcogenides. TMDs for short.
TMDs. Okay, that sets the stage perfectly. So for our deep dive today, our mission is, let's explore this incredibly exciting emerging field.
Let's do it.
We'll get into the fundamental science behind these 2D materials, unpack the significant engineering hurdles, because there have to be some.
Oh, yeah, big ones.
And look at the future trajectory, where this is all going. And ultimately, let's talk about what this revolutionary shift could mean for you, for the technology you use every single day.
Sounds good.
All right, let's unpack this looming crisis in silicon first. It sounds like the move beyond silicon isn't about one single failure point. It's more like a chain reaction.
That's precisely it. It's been described as a cascade of interconnected physical failures, right down at the nanoscale. It's a real vicious cycle.
How so?
Well, you solve one problem, maybe leakage, and the fix you implement often makes another problem worse, like heat or maybe contact resistance. It's like patching one leak in a dam, and then another one just springs up right next to it because of the pressure.
Okay, and at the heart of this is the transistor itself, right? The MOSFET. We keep trying to make these switches unbelievably small. What actually happens when you shrink that transistor channel down to just a few nanometers?
Well, think of your transistor like a tiny gate, okay, controlling water flow or electron flow between a source and a drain.
Got it.
As we shrink that channel length down to nanometers, the gate, which is supposed to be the boss, the perfect controller, it starts losing its grip.
Okay.
And this leads to what engineers call short channel effects,
Yeah.
SCEs.
So the switch gets leaky even when it's supposed to be shut off.
Exactly. That's a great way to put it. A prime example is something called Drain-Induced Barrier Lowering, DIBL. Yeah. Because the drain end is just so incredibly close to the source end now, it actually starts to pull electrons through the channel, even when the gate is saying, stop, be off.
Like a magnet pulling a door open is a crack.
Sort of, yeah. Letting it trickle through. And the consequence is a degraded subthreshold swing.
Okay, subthreshold swing.
Yeah.
What does that mean practically?
It just means it's much harder to clearly turn the transistor on or off with a small change in voltage. The switch gets mushy, less decisive.
Right, which hits performance and power use.
Both. Big time. And that takes us right into the power crisis. We used to worry mostly about dynamic power used when switching.
Yeah, active power.
Right.
Yeah.
But now, in these incredibly tiny, dense chips, static power, the power just wasted when the circuit is sitting idle from all that leakage that's become a huge, persistent problem.
Because there are billions of these leaky transistors just humming away, even when idle.
Billions. And that subthreshold leakage from short channel effects is a major culprit.
Mm.
And then there's this other fundamental barrier. It's almost like a speed limit set by physics itself. Physicists call it the Boltzmann tyranny.
Boltzmann tyranny? Sounds serious.
It is, for chip designers. In simple terms, it means there's a theoretical limit to how efficiently you can turn off a transistor at room temperature. About 60 millivolts per decade change in current.
Okay.
So you can't just keep lowering the operating voltage to save power, because below a certain point, the off-state leakage current just skyrockets exponentially. And since power goes as voltage squared...
You hit a wall. You can't lower voltage further without massive leakage.
Exactly. A real hard limit for power reduction in conventional transistors.
And what's really interesting here, almost ironic, is how the industry tried to fix the other problem, the short channel effects. They made the gate insulator thinner, right?
They did, to get the gate closer electrically to the channel and improve control. Traditionally, it was silicon dioxide. They made it thinner and thinner. By the 65 nanometer node, it was down to just 1.2 nanometers.
Which is what, like 5 atoms thick?
Fewer than 5 atomic layers. Insanely thin.
But that created a whole new problem.
Oh, yes. This fix inadvertently opened Pandora's box. Quantum mechanical tunneling kicked in. At that scale, electrons don't need to jump over the energy barrier of the insulator anymore. They can just tunnel right through it. Kind of magic. Sort of.
Which means more leakage?
Substantial gate linkage current, yeah. Directly from the gate, through the insulator, into the channel, wasting power in a totally new way. And this really highlights that cyclical nature of silicon's failure. Solving one leakage path created another major one.
Wow. Okay, so you've got leakage from short channels, leakage through the gate insulator. All that wasted power has to go somewhere. And that means heat, right?
Exactly. Heat. We're talking billions of transistors packed into a space the size of your fingernail. Maybe smaller. The thermal bottleneck is immense.
There must be a physical limit.
There absolutely is. Current estimates suggest silicon chips just can't dissipate the heat effectively if transistors are packed denser than about the 5 nanometer equivalent. Beyond that, you risk thermal runaway, device failure.
Yeah.
Meltdown, basically.
And that explains why clock speeds stalled.
Precisely. That's why Dinard, scaling the principle that said power density stays constant as transistors shrink, essentially broke down around 2006.
Yeah.
We kept packing more transistors on chips, thanks to Moore's law.
But couldn't run them any faster.
Couldn't crank up the clock frequency because of the heat. So transistor counts went up, but single-core performance increases slowed dramatically. That thermal limit is a really defining hard wall for conventional silicon.
So silicon's hitting this wall. Multiple walls, really. Leakage, power, heat. It sounds like we can't just keep doing the same old thing. The industry has to rethink the materials themselves. Is it about finding one magic bullet material to replace silicon or something else?
It's definitely not a one-size-fits-all replacement scenario. That's probably not going to happen. This is a bigger shift, a fundamental move toward strategic diversification.
A new palette for electronics.
That's a great way to put it. A whole new palette. We're moving from relying on just silicon to choosing different materials based on their specific strengths.
Yeah.
And right at the forefront, for digital logic at least, are these transition metal dichalcogenides, the TMDs.
Okay, TMDs. What exactly are they, and what makes them so special for this?
So their compounds, their chemical formula, is typically MX tauntrunners. The M is a transition metal. Think molybdenum, tungsten.
Okay.
And the X is a chalcogen sulfur, selenium, tellurium. So familiar examples are molybdenum disulfide, MOF-acetophaser, or tungsten diselenide, WSE22s. Their defining feature is this layered crystal structure. Inside each layer, you've got strong covalent bonds holding the atoms together, nice and stable. But between the layers, only very weak van der Waals forces, like sheets of paper weakly stuck together.
Ah, so you can separate the layers.
Exactly. That's the magic. It allows us to isolate stable, single-atom thick layers. A monolayer of MOS-22, for instance, is only about 0.6 nanometers thick, just incredibly thin.
And you can actually peel them off. I read something about using tape.
Yeah, the initial discovery in a lot of lab work uses micromechanical exfoliation.
Yeah.
Literally using Scotch tape to peel off layers until you get down to a single one.
Yeah.
Amazing science, but
Not exactly factory friendly.
not scalable, no. But it proved the concept. And it's this ultimate thinness, this 2D nature, that gives them such potentially superior electronic properties for transistors.
Right, so what does that atomic thinness actually do for them electronically? How does it beat silicon at its own game, potentially?
That is the absolute key. First, that atomically thin body provides the ideal geometry for a transistor channel.
How so?
In traditional silicon, the gate's electric field tries to control the channel, but it only penetrates so far into that thicker silicon body, right? The parts deeper down are less controlled.
Which leads to those short channel leakage problems.
Exactly. But in a 2D field effect transistor, or FET, the entire channel is essentially a surface. It's all right there, exposed to the gate.
So the gate has much better control.
It allows the gate to exert near-perfect electrostatic control over the entire volume of the channel. It can clamp down on leakage much more effectively. That directly suppresses things like DIBL and lets you maintain a sharp turn-on, a good subthreshold swing, even at tiny dimensions.
Okay, so the gate can really grab hold of all the electrons, clamp down tight, unlike in thicker silicon where some might slip past underneath.
Precisely. And there's another huge plus, their surfaces.
Ah, yes. You mentioned silicon has dangling bonds.
Yeah, when you make silicon really thin, or create surfaces, you inevitably break chemical bonds, leaving these unsatisfied, dangling bonds. They act like sticky traps for electrons flowing through the channel. They scatter the charge carriers, slow them down, hurt performance.
Like potholes in the road?
Good analogy. But 2D materials, when they're grown properly, have naturally pristine, chemically inert surfaces. Almost no dangling bonds.
So a smoother road for electrons.
A much smoother road. This minimizes carrier scattering and holds the promise for much higher electron mobility, meaning faster potential devices.
That makes a lot of sense. Now, beyond just speed and efficiency, there was another really fascinating 2D material you mentioned, black phosphorus.
Ah, yes, black phosphorus.
It has this remarkable property, reconfigurable transistor polarity. What on earth does that mean, and why is it important?
It means a single transistor made from black phosphorus can dynamically switch between being N-type, conducting with electrons, and P-type, conducting with positive holes.
The same transistor can be both. Yes. Not at the same time, but you can switch its mode just by applying a voltage to a separate control gate. Flip it from N-type to P-type and back again.
Okay, that sounds fundamentally different. What are the implications? Why would you want to do that?
Well, this opens up completely new possibilities, especially in hardware security.
Security? How?
Imagine building logic gates where the function isn't fixed in the hardware. You could create camouflaged logic, circuits that can change their function on the fly. This makes it incredibly difficult for someone to probe the chip, analyze its physical layout, and figure out what it's actually doing. Reverse engineering becomes a nightmare.
Wow. So you could hide the circuit's true function?
Potentially, yes. Or build circuits that can adapt. It highlights this really significant strategic shift we talked about earlier. We're moving towards a toolbox of specialized 2D materials. MOSFETs 2D2 for performance, maybe black phosphorus for security. Picking the right tool for the job. Okay, so we've got these amazing materials, incredible properties shown off in labs. But like you said, getting them from a lab bench into mass production, into the fabs, making billions of chips, that's the monumental engineering challenge.
Huge, absolutely huge.
Because the silicon world is top-down subtractive, right? Carving stuff away. But 2D needs a bottom-up additive approach. Can you elaborate on that difference? Why is it such a hurdle?
Yeah, it's a fundamental paradigm shift. Think of silicon manufacturing like sculpting from a block of marble. You start with a big, perfect silicon wafer, and then you use lithography to define patterns. You etch away material, you deposit thin films, you implant ions for doping. It's all about precisely removing and modifying the bulk crystal.
Highly refined over decades.
Incredibly refined. But 2D materials are more like building with atomic Lego bricks. You have to grow the material layer by layer, atom by atom ideally, right onto the wafer. You're adding material in precise locations. It requires completely different tools, different chemistry, different process controls, things the multi-billion-dollar silicon fabs just aren't designed for right now.
And the very first step for 2D is just making the material itself reliably at scale. That tape method, micromechanical exfoliation, obviously not the answer for industry.
Right. Great for science, produces beautiful, pristine flakes, but inherently non-scalable. You can't build an industry on sticky tape.
So what's the industrial solution?
For commercial production, the focus is on wafer-scale synthesis. The leading techniques are chemical vapor deposition, CVD, and a related one, metal-organic chemical vapor deposition, MOCVD.
CVD and MOCVD,
Okay.
how do they work?
Basically, you flow precursor gases containing the necessary elements like molybdenum and sulfur for MOS-2 into a high-temperature furnace containing your wafers. The gases react and decompose on the hot wafer surface, depositing a thin film of the 2D material.
Sounds straightforward, but I bet it's not.
Oh, the devil is in the details.
Yeah.
The huge challenge is getting large area single crystal films. You want the atomic lattice perfectly aligned across the whole wafer, or at least over large domains, and you need incredibly low defect density, all while doing this at high temperatures, often over 500 Celsius, and retaining that perfect, pristine material quality. It's a very delicate balancing act between growth speed, scale, and crystalline perfection.
Okay, so let's say you managed to grow a decent wafer-scale 2D film. Then you need to actually build transistors on it. And you mentioned some critical hurdles there. A big one was reducing contact resistance, RC.
Yeah.
Why is that so tough for 2D materials?
Yeah, this has been a persistent thorn in the side for 2D electronics, a severe bottleneck. Imagine you had this amazing 2D material, a superhighway for electrons,
Right.
but the electrons have to get onto that highway from the metal wires, the contacts. And often, at that junction between the metal and the 2D semiconductor, there's an energy barrier. It's called a Schottky barrier.
Like a toll booth slowing things down.
Exactly like a toll booth. It impedes the flow of electrons, creating high resistance right at the point of entry. This contact resistance can actually be much higher than the resistance of the 2D channel itself, completely dominating the device's performance. It doesn't matter how good the channel is if you can't get current in and out efficiently.
But wasn't there a breakthrough on this? I remember reading about MIT, Berkeley, TSMC using bismuth.
Ah, yes. That was a landmark study. They showed that by using semi-metallic bismuth as the contact material for a Boltzmann 2.2, they could achieve ultra-low, barrier-free contact resistance. Essentially, they eliminated the toll booth for that specific combination.
That sounds huge. Did it solve the problem?
It was a massive proof of concept. It showed it is possible to get contacts as good as or even better than silicon. But that was for one specific material pairing, Limas 2.2s. Finding similar low-resistance, reliable, and manufacturable contact strategies for the whole zoo of other promising TMDs is still a major ongoing research effort. It's not a universally solved problem yet.
Okay, so contacts are one hurdle. What else? You mentioned doping.
Right. Doping, adding impurities to control whether the semiconductor is N-type or P-type. In silicon, we use ion implantation, basically shooting high-energy ions into the crystal.
Doesn't sound very gentle.
It's not. And it's totally unsuitable for atomically thin 2D layers. You would just blast them to pieces, like trying to etch fine details onto a single sheet of paper with a sandblaster. Way too destructive.
So how do you dope 2D materials?
We need new, non-destructive strategies. Things like surface charge transfer doping, where molecules sitting on the surface donate or accept electrons, or in situ doping, where you introduce the dopant atoms during the CVD growth process itself.
But getting that right must be hard, like getting enough dopants in, evenly spread.
Exactly. Achieving the high concentrations needed for real devices with good uniformity across the wafer and making sure it's stable over time. That's still a formidable challenge for industrial scale.
And then there's the gate insulator again, the high dielectric. Silicon dioxide is out, we need better insulators, but getting them onto 2D materials is tricky.
It is, because those pristine, chemically inert surfaces we liked for electron transport, they ironically make it hard for the chemicals used in standard atomic layer deposition, ALD, to stick and form a uniform, high-quality dielectric film.
ALD is the main technique for depositing these thin insulators, right?
Yes, it's the industry standard, but it relies on chemical reactions with the surface. If the surface is too inert, the deposition can be patchy, non-uniform, full of pinholes. It's like trying to paint on Teflon. You need special surface treatments or new deposition techniques, another big engineering problem to solve.
Okay, contacts, doping, dielectrics. And overarching all of this, you mentioned the biggest challenge for actually making money from this: yield and variability.
Absolutely. This is the elephant in the room for any new semiconductor technology. In the lab, researchers can make a few amazing hero devices, pick the best ones, and publish great results.
Right.
But a commercial chip needs billions of transistors, and they all need to work correctly and work very similarly to each other. Any small variations in the 2D material quality, the layer thickness, the contact resistance, the doping level across a large wafer, these can lead to huge differences in transistor performance.
So one transistor might be fast, another slow, another might not switch at all.
Exactly.
Right.
If the device-to-device variability is too high, your yield of functional chips plummets, and the economics just don't work. You can't sell chips if only 10% of them meet spec.
That Penn State work you mentioned, building a simple computer with over 1,000 transistors, that was a big step towards tackling this.
A crucial first step, yes. because it moved beyond just characterizing single hero devices and started looking at the statistics, the variability, the integration challenges of building a functional system at a somewhat larger scale. Proving consistency in yield is paramount for commercial viability.
Let's zoom in then on the structure of a single 2D transistor. It's still a field effect transistor, a FET, source, drain, gate. The basics are the same.
Fundamentally, yes.
But the key architectural advantage, you said, is that ultra-thin body of the 2D channel. Remind us again why that thinness is such a big deal electronically.
It comes back to electrostatic control. In a bulky silicon transistor, the gate's influence fades as you go deeper into the channel. The bottom part isn't controlled as well as the top surface,
leading to those short channel effects, the leakage.
Right. But in a 2D FET, the channel is all surface. It's just that single atomic layer. So the gate's electric field can effectively control the entire volume of the channel. It gets near perfect electrostatic authority. Think of it like trying to control a thick book versus a single sheet of paper. It's much easier to influence the entire sheet.
So you can clamp down on leakage much more effectively, even when the channel is very short.
Precisely. That's the core benefit for scaling, maintaining good switching behavior at dimensions where silicon really struggles.
And the ultimate goal isn't just one perfect transistor, it's building a whole computer, which usually means CMOS technology, right? Complementary metal-oxide-semiconductor.
Yes, CMOS is the workhorse of digital logic today.
Because it uses both N-type transistors, which conduct electrons, and P-type transistors, conducting holes, working together in pairs.
Right, and the key advantage of CMOS is its very low static power consumption. When one transistor in the pair is on, the other is off, so there's almost no path for current to flow when the circuit isn't actively switching. Hugely important for power efficiency.
So has anyone actually built a full CMOS computer using only 2D materials?
They have. That Penn State work we keep mentioning. That was the landmark achievement. The first fully functional CMOS computer built entirely from 2D materials.
That's incredible. What did they use?
They used MOCVD, that scalable growth technique, to grow large sheets of bucket 2 for the N-type transistors and WSE2 tungsten diselenide for the P-type ones.
And how complex was it?
They fabricated over 1,000 of each type of transistor and integrated them to build circuits that could perform basic logic operations. It ran at low voltage, low power, clocked at about 25 kilohertz.
Okay, 25 kilohertz isn't going to break any speed records.
No, not yet. But that wasn't the point. The huge significance was proving that all the necessary components for a functioning CMOS system, N-type FETs, P-type FETs, interconnects, working together, could actually be realized on a scalable all-2D platform. It showed it's possible.
A foundational proof of concept. Huge milestone.
Absolutely. Foundational is the right word. And speaking of foundations, as we get down to these atomic scales, something interesting happens with quantum mechanics. Quantum tunneling.
Right.
We talked about it as a villain, causing leakage in silicon gate insulators.
Right, a foe.
But in the world of 2D materials, it can also potentially be a friend. It takes on this fascinating dual role.
Okay, so it's still a foe when it causes unwanted leakage, right? Like maybe electrons tunneling directly from source to drain if the channel gets too short?
Yes, that's definitely a concern. Or tunneling through very thin gate dielectrics on top of the 2D material. It can create a floor for the off-state current, limiting how low you can get it, which wastes power.
But how can tunneling be harnessed as an operational principle? You mentioned TFETs, tunneling field effect transistors.
Exactly. TFETs work on a completely different physical principle than conventional MOSFETs.
How so?
MOSFETs rely on thermionic emission, basically giving electrons enough energy to jump over an energy barrier controlled by the gate. TFETs instead work by modulating band-to-band tunneling.
Band-to-band tunneling.
It means electrons tunnel through a thin energy barrier within the material itself, from the valence band to the conduction band. The gate voltage controls how likely this tunneling is.
And why is that advantageous?
Because theoretically, this tunneling mechanism can turn on much more abruptly with voltage than thermionic emission. TFETs have the potential to bypass that fundamental 60 millivolts per decade subthreshold swing limit of MOSFETs at room temperature.
Which means they could switch much more sharply.
Potentially achieve much steeper switching, yes, which could lead to ultra-low power operation because you could run them at much lower supply voltages while still keeping the leakage current low.
And 2D materials are good for this?
They're considered ideal platforms. Especially 2D heterostructures where you stack different 2D materials on top of each other. You can carefully engineer the energy band alignment between the layers to create the perfect conditions for efficient band-to-band tunneling.
So what's the big takeaway here? It sounds like the field is shifting. We're not just fighting quantum mechanics anymore. We're trying to harness it. Use it.
Precisely. That's a perfect summary. At these scales, quantum effects are unavoidable. So instead of just trying to suppress them as annoyances, the goal is increasingly to actively design devices that rely on quantum phenomena for their operation. 2D materials offer this incredible playground to explore both improved classical devices and entirely new quantum devices like TFETs.
Okay, so we're shrinking things laterally with 2D materials, but the industry is also going vertical, right? Building upwards. Why is that necessary? Even with perfect 2D transistors, does a purely flat chip hit limits?
It does, eventually. The problem shifts from the transistors themselves to the connections between them, the interconnects.
The wiring?
Yeah, tiny metal wires. As you pack billions, trillions of transistors onto a flat chip, that wiring becomes this incredibly dense, tangled, well, you called it a spaghetti-like web. And those wires have resistance and capacitance. Longer wires mean more delay, more power consumption. The interconnects themselves become the bottleneck, limiting speed and efficiency no matter how good the transistors are.
So going 3D helps solve the wiring problem.
That's a major driver. By stacking layers of circuits vertically, you can dramatically shorten the connections between them. Instead of a long horizontal wire across the chip, you might just need a short vertical connection, called a via, going straight up or down to the next layer.
And shorter wires mean?
Less resistance, less capacitance. Studies show you can reduce average wire length by 50% or more. That translates directly into lower power consumption, maybe up to 51% reduction in some cases, and potentially much higher clock frequencies, maybe 3, almost 4 times faster in ideal scenarios. Plus, higher density, more transistors in the same footprint.
The industry is already moving this way with the transistors themselves, isn't it? FinFETs first.
Exactly. FinFETs, which became mainstream around the 16, 14 nanometer nodes, turned the channel into a vertical fin, and the gate wraps around 3 sides of it. Better control than planar.
And the next step is gate-all-around, GAFETs.
Right. That's coming in now at the sub-5 nanometer nodes. Here, the gate completely surrounds the channel, often in the form of stacked horizontal nanowires or nanosheets. This gives you ultimate electrostatic control over the channel, the best possible gate geometry, really.
But there's a catch with these vertical structures, isn't there? Heat again?
Yes. The big challenge with both FinFETs and especially GAFETs is self-heating.
Because it's harder for heat to get out.
Exactly. These are tiny, confined structures. Heat generated in the channel doesn't have an easy path out. GAFETs, where the channel is fully enclosed by the gate, tend to suffer more. One study showed like a 17 Kelvin temperature rise in a GAFET compared to 12 K for a similar FinFET under load. That's significant. Heat management becomes critical.
Okay, so if we put these pieces together, we have amazing 2D materials for the channel, and we have advanced 3D transistor structures like GAFETs. Is the ultimate goal to combine them?
That's where the cutting edge is heading, yes. Imagine a gate-all-around FET where those channel nanosheets aren't silicon, but are made from an atomically thin 2D material like Muscovite or WSE2 inner.
Wow. Best of both worlds.
That's the idea. You get the unparalleled electrostatic control from the 2D material's thinness, combined with the superior gate geometry of the GAFET structure, and the density benefits of building these things vertically in a 3D integrated circuit.
Is this what they call monolithic 3D integration, M3D?
Yes, M3D is the concept of fabricating multiple layers of active devices directly on top of each other on the same starting wafer. Critically, they're connected by these ultrafine monolithic inner-tier vias, or MIVs.
MIVs. How are they different from older 3D stacking connections?
They're much, much smaller and denser. MIVs can be less than 0.1 micrometers across, whereas the older through-silicon vias, TFVs, used for chiplet stacking, are more like 1 to 5 micrometers. MIVs allow for much finer-grained, denser vertical connections between layers.
So M3D with 2D GAFETs sounds like the ultimate combination. Huge potential benefits in power, density, maybe cost. But what's the biggest challenge holding that back?
Well, besides the complexity of actually manufacturing such a thing, the greatest challenge for M3D, especially dense M3D, comes right back to
heat.
Heat. Severe thermal issues. You're generating heat in multiple stacked layers, and it all has to find a way out through the bottom silicon wafer. Managing that heat concentration is incredibly difficult. Plus, the design complexity goes way up when you're routing signals and power vertically between layers. So massive potential, but also massive engineering challenges.
Okay, so let's talk benchmarks. Where do things stand now? The Penn State 2D CMOS computer ran at 25 kilohertz. That's the state of the art for a full system, right? A fantastic proof of concept, but obviously miles away from silicon speeds.
Right. For a fully integrated 2D system, that's a key benchmark, yes. Shows integration is possible. But it's not representative of the potential speed of individual 2D transistors yet.
So what do simulations predict if we could build those stacked vertical JFETs using 2D materials? What's the payoff compared to current silicon?
Well, looking ahead, sophisticated simulations like SPICY models are predicting significant gains. For example, projections suggest that 2D material-based stacked GAFETs could potentially offer around an 18% performance boost and maybe a 31% improvement in energy efficiency compared to the 7-nanometer silicon FinFETs that are common today.
Okay, 18% performance, 31% energy efficiency. That's definitely worthwhile.
It is. And those kinds of projections are crucial for guiding the research and justifying the huge investment needed to develop these technologies.
Now, what's really fascinating here, I think, is that while replacing silicon in high-performance computing is the ultimate prize, these 2D materials have other unique properties, which makes them suitable for a whole wide range of other applications. It might not be a case of replacing silicon everywhere all at once, but more of a phased adoption.
That's a very likely scenario. You'll see 2D materials carving out niches where their unique advantages really shine, even if silicon remains dominant elsewhere for a while.
What kind of niches are we talking about? Where might 2D offer something silicon just can't do?
Well, think about analog and RF electronics for communications. Their properties could lead to better linearity or higher frequencies. Non-volatile memory is another area. Neuromorphic computing building chips that mimic how the brain processes information for AI 2D materials offer interesting possibilities there.
And sensing. Their thinness must make them super sensitive.
Extremely sensitive. Their huge surface area to volume ratio makes them ideal for detecting tiny amounts of chemicals or biological molecules. Ultra-sensitive sensors. And of course, hardware security, like we discussed with the reconfigurable black phosphorus FETs. These are potential killer features that silicon struggles to match.
So these other markets, sensors, security, maybe specialized memory, they could see commercial success for 2D materials much earlier, even if the volumes aren't as massive as CPUs initially.
Exactly. It allows the technology to mature, the manufacturing processes to improve, and costs to come down while providing real value in specific areas. It's a pathway to broader adoption.
But that roadmap to commercialization, it's still long, right? We need to be realistic. Silicon has had, what, 80 years of development?
Easily.
Yeah.
Maybe more if you count the early semiconductor physics. Intensive research into 2D electronic materials really only kicked off in earnest around 2010 after graphene burst onto the scene. That's a massive maturity gap.
So closing that gap needs a huge coordinated effort.
Absolutely. It requires concerted R&D involving academia, major industry players, startups, and government funding agencies, and consortia like the 2D Crystal Consortium Materials Innovation Platform, the 2DCC MIP you mentioned in the sources. They play a vital role in developing the material synthesis, the fabrication processes, the characterization tools needed to achieve reliable, wafer-scale, high-yield manufacturing.
So the ultimate goal is really driving the transition of 2D semiconductors from the laboratory to real-world VLSI scale applications. VLSI meaning very large-scale integration, billions of transistors.
Precisely. It's an enormous task, crossing the valley of death from lab discovery to industrial reality. But the potential payoff continuing the progress of computing technology, enabling entirely new applications, is truly transformative.
So let's try and bring this all together. We've journeyed from the impending end of conventional silicon scaling Moore's law running out of steam.
Hitting those physical walls, yeah.
Through the emergence of these remarkable 2D materials as a potential, maybe even likely transformative solution. And we've looked at the very real, significant engineering hurdles that still need to be overcome.
Contacts, doping, growth, yield, heat. The list is long, but progress is being made.
And it seems clear the post-silicon era won't be about just one material replacing another. It's going to be defined by material diversity and architectural ingenuity.
That's the key takeaway, I think.
Yeah.
It's not a simple swap. It's about building a much richer toolbox. creating platforms for heterogeneous, meaning mixed materials, vertically integrated, so 3D, and functionally diverse electronic systems. Different materials for different jobs, all working together.
And that synergy, that combination of 2D materials with advanced 3D architectures like GEFETs and potentially monolithic 3D integration, that really seems to be the pathway forward.
It looks like the most promising road to continue scaling performance and efficiency, yes, combining the best of material science and device architecture.
So as we stand here, really at the dawn of this potential shift, here is something for you, our listeners, to think about. The engine of our digital world, the chip, desperately needs new fuel to keep advancing. This journey for 2D materials, from the lab to the fab, it's going to be incredibly challenging, no doubt. But it holds the promise of extending that spirit of Moore's law for potentially decades more.
It really does.
So consider this. How might this fundamental shift in the building blocks of electronics change the way you interact with technology day to day? Could it enable entirely new forms of computing, maybe artificial intelligence, things we can barely even imagine right now? Or, conversely, what might be the unforeseen challenges, the unexpected roadblocks that arise as we transition from relying on one well-understood material, silicon, to this diverse, complex palette of atomic-scale building blocks? Lots to think about.